I'm on the east coast of Scotland on a rather stormy day overlooking St Abbs Harbour behind me. On a day like this, the enormous power of the sea is all too obvious. Scotland is at the forefront of research into developing new technologies for harnessing this power. I've come to the Scottish island of Islay to look at the first wave power machine which actually produced energy which was fed into the grid. It's called the Limpet, and as the name implies, it's actually built into the rocks. Limpet is an oscillating water column device. Inside this structure is a massive concrete chamber, and as the waves come in and out, the water level rises and falls within the chamber and compresses and decompresses the air above. And it's this air which activates the turbines which generate the electricity. In a minute, I'll go inside and have a look at the turbines. Kevin here is the maintenance engineer for this system, and he's kindly shut off one of the turbines so we can actually see it. This, Kevin, I think is a Wells turbine, is that right?
Yeah, that's correct.
And one of the fantastic features of this is that it's self-rectifying, and it actually works just as well if the flow's coming out one direction or in the other one.
Right.
Could you just show us inside? As far back as the early 1970s, Stephen Salter at Edinburgh University was experimenting with wave power devices.
Everybody who thinks about waves thinks about them going up and down. This was the very first model that I made. Rotated about here, gadget here to join it up to a dynamometer to measure forces and velocities. And this wasn't very efficient until I tipped it like that. So it looks as if the slope motion is a whole lot better. We did lots of messing around. The most important step was to have this model rotating about the point here, but because this is cylindrical, coaxial with this axis here, it doesn't make any waves behind. And this model was able to get 90% of the energy out of the waves. You saw calm water behind. We then had to think of ways of giving this a reaction, something to push against. And we thought the best way was not a tower going into the seabed, but a very long spine. And we built a whole group of models like this. See there's a power takeoff there. And because they're spanning many different wave crests, some up, some down, you get a stable average reference, but you can make the spine bend if the waves get too big, so that it is no longer trying to be stiff. It's rolling with the punch for waves more than about 3 meters high.
Nature has been very good to us in Scotland. We sit off the northeast Atlantic, and this has given us some of the most energetic waves in the world. We also sit between two of the world's great tide generating systems, and this has given us some of the most energetic tidal currents. The Pentland Firth, for example, is recognised as one of the 3 most energetic zones that we have worldwide.
The Seagen and Hammerfest-Strom tidal energy converters have blades similar to those used on wind turbines to convert the kinetic energy of the tidal stream into electrical energy, taking advantage of the predictability of tidal flow. In the Scott Renewables system, instead of the turbine being fixed to the bed, the blades are lowered beneath a floating structure. This turbine has been towed into harbour for servicing.
My name's Deborah Smith and I'm Marketing Coordinator at Polamis Wave Power. I'm standing now next to one of our Polamis P2 units, which is currently in the final stages of commissioning at our quayside here in Leith Docks in Edinburgh. The Polamis is made up of 5 tubes, which are linked by hinge joints. It's the movement between those 5 tubes which generates electricity. Polamis gets its name from Polamis platurus, a species of sea snake, due to the way it moves in the water and its long, thin shape.
My name's Nick Pelosi, Senior Production Engineer at Palamis Wave Power. Here we are inside one of the 4 power conversion modules that makes up the Palamis Wave Energy Converter. It's inside here that the electricity is generated prior to it being fed back into the national grid via subsea electrical cable. The motion of the Palamis is resisted at each joint by hydraulic rams. These hydraulic rams pump high pressure fluid into storage accumulators, which you can see here behind me. We can then release this stored energy in a controlled fashion back into hydraulic motors, which subsequently turn electrical generators to produce the electricity.
I've come out to Crew in the Orkney to visit the aquamarine power system here, and I want to introduce you to David Cousins, who's the operations manager here. Is that right?
That's
David?
correct, yes.
Could you just explain how this system operates behind us?
Sure. The system behind us is the power takeoff system for the Oyster 800 wave energy converter. We take the high pressure water feed from the Oyster and we pass it through a conventional Pelton turbine behind you, and that's also linked to a flywheel and a generator.
Okay, now the flap from the Oyster gives a sort of pulsatile flow, is that correct? So is that a problem for this Pelton wheel turbine?
You're correct, the flap moves according to the wave period, and the pulses from that are smoothed out by a series of accumulators offshore and onshore, and we've also got a flywheel to maintain a constant shaft speed.
And what sort of power will this unit generate?
A single Oyster flap is rated at 800 kilowatts. This drivetrain behind you is rated at 1.2 megawatts.
The University of Edinburgh already has a very sophisticated multidirectional wave basin. We call it the curved tank. We can use this to simulate random waves in a wide range of directions. However, we're in the process of building a much larger facility called FlowWave, which will enable us to superimpose waves and currents, and also over a wide range of directions.
My name is Stuart Brown. I'm standing outside the new FlowWave facility being built in Edinburgh. This new facility will be opening later in the year and is designed to replicate sea conditions of wave and tide anywhere around the UK coastline.
I'm in the FlowWave tank. I'd like to introduce you to Matthew Ray, who's Director of Edinburgh Designs, who are making the wave makers for this facility. Matthew, could you tell us a little bit about the wave makers?
Yes, of course. This is a unique facility in that we have got wave makers that go all 360 degrees round the tank. So in total we have 168 wave machines, identical wave machines like this, and they go all the way round. They act on the water in front, and then there's a dry passageway which we can walk through to maintain and look after the machines. In the middle of the tank we've got a series of current generators which can generate current from any direction. We can either go from north to south or east to west, or change dynamically as we progress through the experiment. We're now here at the base of the tank. Now imagine that there's going to be a big floor that separates the top part of the tank from the lower part of the tank. Water is moved from the top part to the bottom part by these big ducts, and there's 28 of them in a circle all the way around the tank. So we've got a big propeller here that we draw the water in. The water comes down here and is turned through this turning vane and then up, introduced below the wave makers and back into the top section.
The wind people are way ahead at the moment, thanks I think largely to Danish politics. We've got to catch up with waves and tidal streams. I think that in the near term the tidal stream will be bigger and quicker, but eventually the resource from the wave power offshore will be perhaps double the tidal stream.